Good morning everyone. So welcome to class number 5. So last day we were discussing about the Dirac notation and the Bra and Ket notation, and we discussed that any vector or any wave function as described in the eigenstate space of an operator can be represented in terms of a matrix. Okay, so if we write this beta, so beta is basically the wave function, and if it contains three components of the basis elements or three components of the eigenfunction space, it can be written as beta equal to C1, C2, C3, and which is equal to C1 psi 1x plus C2 psi 2x plus C3 psi 3x. So if we basically write psi 1x in vector notation or Ket notation, so this would basically become psi 1 equal to 1 0 0. Okay, right now we are considering that we only have three bases. The set of basis vectors contains three elements. Okay. Okay. So this thing can also be written in this form, like beta, which is equal to C1 C2 C3. This is equal to C1 1 0 0 plus C2 0 1 0 plus C3 0 0 1, and instead of writing it in this form, we can also write it like this. So these are all equivalent methods of representing a wave function, and all of them are basically equivalent. Okay, and we also denoted the complex conjugate of this wave function beta as this Bra notation. So the previous one was the Ket, this was Ket, and this one is the Bra part, and this is written as a row vector. And what do is we basically take the complex conjugate transpose of the column vector. Okay, so we take the complex conjugate and we also transpose the row vector. So C1 star, C2 star, C3 star. So this star basically indicates complex conjugates, and then we transpose it, so this column vector basically becomes a row vector now. Okay, and if we are using an orthonormal basis, which is the case if we are using the eigenstates as a basis, in that case the inner product between two vectors is basically defined by this term beta m beta n, which is equal to, let us say, C1m star, C2m star, C3m star multiplied by this column vector C1n, C2n, C3n, which basically becomes equal to C1m star C1n plus C2m star C2n plus C3m star C3n. Okay, so again this part is valid only when we use an orthonormal basis set. Okay, So now, how do we write the average value of an operator? Okay, let us not right now go into the average value of an operator, but let us actually discuss something else. So we have basically seen ways to represent the wave functions in bracket notation. Now, how about the operators? So bracket notation is nothing but the matrix notation. Okay, so how about the operators? So now we already know that any linear operator in a vector space can be represented as a matrix. Okay, this is a well-known fact that any linear operator in vector space can be represented as a matrix. Now, what is the meaning of this term linear operator? So, linear operator basically means if I have an operator Q, then Q acting on this, let us say, two wave functions beta 1x, Q operator acting on the wave function beta 1x plus beta 2x is equal to the sum of Q acting on the wave function beta 1x plus the operator Q acting on the wave function beta 2x. Okay, so this is what a linear operator basically means. So linear operator must satisfy this property. Okay, and fortunately any or almost all the operators that we use or that we come across in quantum mechanics are linear operators. Okay, for example, this operator del 2 del x2 that we encounter in the Hamiltonian, this is basically a linear operator. Okay, so fortunately all the operators or almost all the operators that we come across in quantum mechanics are linear operators, and therefore almost all the operators in quantum mechanics can be represented in the form of a matrix. Okay, now so almost all operators in quantum mechanics can be represented as a matrix. So let us call an operator T. So T can be represented in the terms of a matrix in the bracket notation, and we'll see how to calculate the elements of Tm. Now let us say that we represent this integral, okay, minus infinity to plus infinity, or let us say integral over the space which we are considering. It might not always be minus infinity to plus infinity, but we are writing it in a generalized form. So minus infinity to plus infinity, let us call beta m star x, then the operator T acting on beta nx. This in Kate notation, or in sorry, not Kate notation, but in bracket notation or in Dirac notation is represented as this bra m beta m, which is basically this part, and then this part is represented as the Kate, which is T beta n. Okay, so this is basically the inner product between one function beta mx and another function T beta nx. Okay, Now let us consider the matrix version of this operator T, and the matrix version of this operator T must contain all these elements, let us say T11, T12, T13, and we are currently considering that the basis consists of 3 elements. Okay, so we have a 3 cross 3 matrix here, 2 3 T21, T22, T23, T31, T32, T33. Now let us consider an arbitrary element T12. So how do we exactly calculate this element T12 in the matrix? And let us first consider that my basis is basically psi1 x, which is represented in Kate notation as psi1 100, psi2x, which is represented in Kate notation as psi2 equal to 010, and psi3x, which is represented in Kate notation as psi3 equal to 001, and these three are my basis. Okay, so I am assuming just for the sake of explaining things here. Okay, now let us consider this matrix T. So this is our T matrix here. Now I multiply this to the left by psi1, or the vectorial representation of psi1. So let us say 1 0 0, and I multiply to the right. So this is basically psi1. This matrix is our T, or the operator the matrix representation of the operator T, and then I multiply it to the left by the row vector psi2, let us say, okay, or psi2 star actually. So this is basically the Kate format psi2. Okay, now what do I get? So this is so only one element here is 1, and the other two are basically zeros here. So when I do the first row multiplication with this one, I basically get T11. When I do the second row multiplication with this one, I basically get T21, and when I do the third row multiplication with this one, I similarly get T31. So T31. Okay. Now I still have to multiply with another matrix, this one. So 0 1 0. So if I multiply this with this one goes out of picture because it is 0 here, this one goes out of picture because it is 0 here, so there is only one which multiplies this T21. So we basically get T21 over here. Okay, now so T21, let me just write it in another way. T21 is basically 0 1 0, then the T matrix, which I write as the matrix representation of T, times 1 0 0, and this, as I told, is exactly psi1. This, as I told, is exactly this is psi2, and then we have the T matrix. So this is nothing but psi2 T psi1. So we have this part which is T psi1, the Kate of T psi 1, and then we have the bra psi 2 here, so psi 2 over here. Now what does this exactly correspond to? So we have written this thing before, so let me just rub these circular parts over here. So we have written this expression before. Let me go back to this expression. Yeah, so we have this similar expression over here, that T operating on beta n multiplied by this beta star m, okay, is equal to this expression. Okay, so this readily, from this notation we can write this readily as integral over all space psi 2 star x t. So this is the again matrix representation actually. So T operator acting on psi 1 x dx. Okay, so we can generalize this. T mn is equal to integral over all space psi m star x operator T acting on psi 1 x dx, which in Dirac's notation or bracket notation we can write as psi m T psi n. Okay, so this is how we can find the elements of the matrix corresponding to the representation of the operator T. Okay, so now we are almost done with the Dirac's notation part. So we have seen how to represent wave functions in Dirac's notation. We have learned how to represent inner products in Dirac's notation, and we have also learned how to represent operations, linear operation or linear operators in Dirac's notation. So this is basically a matrix. This is basically an integral, and this wave function basically is represented by vector. Okay. Okay. So as I said earlier, that in quantum mechanics the operators correspond to observables and they always should have real eigenvalues, which also means that the operators should be Hermitian operators. And operators in quantum mechanics are Hermitian operators, and Hermitian operators, when they are represented in matrix format, are represented by Hermitian matrix. They are represented by Hermitian matrix. So what is a Hermitian matrix? So a Hermitian matrix basically means that the matrix is equal to its own complex conjugate transpose. So if T is a Hermitian matrix and the complex conjugate transpose is represented by T dagger, then T basically is equal to T dagger. Now what does the complex conjugate transpose means? So we have already seen that this T matrix that we have taken is T11, 12, 13, 21, 22, 23, 31, 32, 33. So this was our matrix T. So what we do is, first we take the complex conjugate of all elements of this matrix, and then we take the transpose of this matrix. So If we take the complex conjugate of all the elements, then this becomes star everywhere, and then we take the transpose. So when we take the transpose, this basically becomes um, so we convert the rows into coulombs, or we convert the columns into rows. So T transpose, T, the complex conjugate transpose of this matrix T basically becomes T 1 star, T 2 star, T 3 star, T 1 star, T 2 star, T 3 star, T 1 star, T 2 star, and T 3 star. So we take the complex conjugate of all the elements, and then we basically convert the columns into row. So this column becomes this row over here. Okay, similarly the second column here becomes this second row, and the third column basically becomes this third row over here. Okay, so that is how we write this complex conjugate transpose, and this is actually T star and not T. Okay, so a Hermitian matrix always has T is equal to the complex conjugate transpose of this of the same matrix T. And how do we actually define Hermitian operators? We have already discussed it earlier, but let us basically discuss it again. So a Hermitian operator T has this property: if T is a Hermitian operator, then T has this property that integral over -infinity to +infinity beta 1x, the operator T, beta 2x, and T is acting on this function beta 2x. This one is equal to integral from -infinity to +infinity T acting on beta 1x. Sorry, this one should be star over here. T acting on beta 1x star beta 2x dx, or in bracket notation, this one is basically beta 1 T beta 2 is basically equal to T beta 1 beta 2. Now this is a slightly stronger condition, and for most books, or for most aspects in quantum mechanics, we actually are happy, or it is actually enough to give this condition. This one is a slightly stronger condition. Another condition which is often encountered in quantum mechanics, or which we satisfy ourselves with, is slightly weaker, and this is basically integral of -infinity to +infinity beta 1x star beta star 1 star x, and this operator T acting on beta 1x dx is equal to integral -infinity to +infinity beta 1x, and this operator T acting on beta 1x dx star. So this we can rearrange and write it as integral -infinity to +infinity T beta 1x star beta 1x dx, which can be written in the form T beta 1 beta 2. Sorry, here also we have beta 1 over here. So this T basically is acting only on this beta 1 here and not on this part basically, okay, and that is the reason I have put third brackets over here, and this complex conjugate, this star, is for this entire function T beta 1 x. Okay. Now since this condition or this condition is actually equivalent to finding out, or let us put it the other way around. Let us take this function over here, that so condition 2 was exactly this integral of minus infinity to plus infinity beta 1 x t acting on beta 1 x dx is equal to the integral from minus infinity to plus infinity beta 1 x, sorry, we had a star over here, t beta 1 x star dx, and this one I can write it as integral minus infinity to plus infinity beta 1 x star t beta 1 x dx, and the whole is then we take the complex conjugate. So this basically comes from the fact that z1 z2, the complex conjugate of z1 z2 is basically equal to z1 times z2 star. So the complex conjugate of the product z1 z2 is basically equal to the product of the complex conjugate of z1 times the complex conjugate of z2. Okay, so this is what we have done here to go from this step to this step over here. Anyway, so now so note that this part is basically nothing but the average value of the operator t for the wave function beta 1, of course. So the average value of the operator t for the wave function beta, or for any arbitrary wave function, because we have not specified beta, so beta is just an arbitrary wave function over here. Okay, there are no specifics, or there is nothing special about this function beta over here. So this is the average value of t for any function or any wave function, let us say, and this is also the average value of t for the same wave function, but we have a complex conjugate over here. So this is equal to the average value of t star. So this is the condition which we wrote earlier when we just wrote that q is equal to q star for an Hermitian operator. Okay, so anyway, that's the criteria. The second condition or the second result is that, just as I said earlier, and I have said this multiple times, from the intuitive argument that the eigen values of a Hermitian operator are real, and since observables in quantum mechanics or observable quantities in quantum mechanics has to be real, therefore all quantum mechanical operators has to be Hermitian, or all quantum mechanical operators corresponding to observables must be Hermitian. Okay, so to verify this fact, let us say that T is a Hermitian operator and F is an eigenfunction of this operator T. Okay, so when we operate this F function with this operator T, okay, we just get some eigen value T times F. So this is the property of an eigenstate for an operator T. Okay, now what we do is we take the inner product of the complex conjugate of this function f with tf, and since this operator t is Hermitian according to the condition which we discussed previously, this should be equal to tf f, right? Now this implies that this tf is equal to this t times f. So this is basically equal to, this t is a number, so it gets out of this inner product, so this becomes equal to t f f. Now this one is basically the bra part, so this is the complex conjugate part basically. Okay, so if we take the complex conjugate of this equation over here, so we basically get, if we take the complex conjugate on both sides, complex conjugate transpose actually, not only complex conjugate, but if we take the complex conjugate transpose of both sides, so let me write it here, complex conjugate transpose of both sides, we basically get tf tf is equal to t star f. Okay, so this part basically is equal to t star f f. Now this cannot be equal to 0, so this cancels out on both sides, so this, from this we basically get t equal to t star. So if a number is same as its complex conjugate, then t must be real. Okay, so therefore t must be real. So we have proved that if t is an Hermitian operator, then the eigenvalues of this operator t are basically real. Okay, so this was the point we were stressing about, and we stressed a lot about it. So this is basically the proof. Now the second important point was that if t is an Hermitian operators, then its eigenstates must be orthogonal. Okay, so to prove this, let us assume that f and g are two eigenstates of t. There can be many more eigenstates, but we are talking about two arbitrary eigenstates of this Hermitian operator t. Okay, now t is an Hermitian operator, so let us talk about this product. If so let us first define the eigenvalues. So the operator t acting on this eigenstate f is equal to, let us say, a times this function f, and this operator t acting on this eigenstate g is a number b times the eigenstate g. Okay, so let us consider this product. Okay, so this is again this is the same, so don't confuse things, please don't confuse things. So this is basically the same as g, this operator tf. Okay, so this part is really equal to this part, and this operator t always acts to the function to its right, so t will act on this f only, both here and here. So these two are equivalent notations actually. Okay, these two are not different. So anyway, so this t acting on this function f produces this eigenvalue a, but a is a number, so a comes out. Okay, and then this is equal to this operator t acting on this function g, and non product with f. So this comes from the property of Hermitian operators that we have seen earlier. Okay, So this property we have already seen earlier. Let us go back to that page. Yeah, this one. So we have this condition for the Hermitian operator which we have discussed earlier. Okay, so this is equal to this TGF, and then this T acting on this eigenstate F produces this number A, but A is a number, so it gets out of the integral and we get A GF, and this is equal to this T operator acting on this eigenstate G produces this number B. Again, B is a number, so it gets out of this integral, so this becomes equal to B GF. Now the inner product of G and F now A and B are non-zero, okay, because these are eigenvalues and these are non-zero basically, okay, because a eigenstate cannot have 0 as the eigenvalue, okay. So since A and B are non-zero, therefore this implies that G, the inner product of G and F, must definitely be equal to 0, which implies that integral of Gx star Fx dx is equal to 0. So Gx and Fx are basically orthogonal. Okay, so we have proved that the eigenstates of a Hermitian matrix are basically orthogonal. And they are not only orthogonal, but they are also complete. So the eigenstates of a Hermitian matrix form a complete orthogonal set. Now the completeness of this set or the completeness of these eigenstates cannot be proved. I mean, it can be proved, but it is very complicated, so we will not discuss it here. But just know this fact that the eigenstates of a Hermitian operator form a complete set, and you can actually represent any function or any valid eigenfunction that operates the suitable boundary condition with the help of the eigenstates of the Hermitian operator. Okay. Now let us see another simple thing, but very important in quantum mechanics. So let us say that I can represent any wave function beta in this vector format. Okay, so C1, C2 and C3, which is basically in space format, it becomes equal to C1 psi 1x plus C2 psi 2x plus C3 psi 3x, where psi 1, psi 2, psi 3 are the eigen states or eigen function or the eigen basis, let us say. Okay. So now how do we calculate C1? We have seen it earlier that C1 is equal to the integral of psi 1 star x beta x dx extending over all the space. Okay, and in bracket notation or in Dirac notation, this becomes equal to psi 1 beta. Okay, so this beta, this wave function can be represented if I replace C1 with this and then C2 with the other corresponding component. So it can be actually generalized like it can be generalized like Cm is equal to psi m beta. Okay, so beta can actually be represented in terms of C1, C2, C3, which is basically equal to psi 1 beta, psi 2 beta, psi 3 beta, and this is just as before equal to psi 1 beta psi 1 So this psi1 is a wave function, but this one is the inner product, so this is basically a number. Okay, so note that this is not a number, this is the kate. So kate is basically represents the wave function itself. So here psi1 is the base, is a component of the basis. So this one is not a number, this is a function, but this one is the inner product. So this one is really a number. Okay, plus psi2 beta, the kate of psi2 plus psi3 beta and the kate of psi3. Now since this is a number, I can actually move it around. So this is equal to psi1 beta plus psi2 beta plus psi3 beta. Okay, so now this total thing can be written as psi1 plus psi2 plus psi3 beta. Okay, so now what we had to the left hand side, I will just go to the previous page. To the left hand side we had this beta. Okay, so this beta is equal to this. So we can cancel this beta on the two sides, and this basically becomes psi1 plus psi2 plus psi3. Now note that we are multiplying beta by this quantity over here. We are multiplying beta by this quantity and we are getting beta. Okay, this is the first point, that we are multiplying a kate vector or a function by this quantity over here and we are getting beta. Okay, so the second thing is that what does this correspond to? Is this a number? Okay, we have already seen that this quantity psi1 this is basically a number because this is the inner product. But what does the other thing, like what does this correspond to? Is this a number? So we can understand that this is not really a number. Now what is this thing? So it would be clear if we represent it in matrix notation. So this one has a vector form, so let us call it 1 0 0, and this one has a row vector from 1 0 0. So this thing is basically a matrix. So it becomes a matrix with all these elements as 0 and only one element as 1. But nevertheless, this is basically not a number but a matrix. Now what does matrix represent in our case? So in our case, matrix basically represent an operator. Okay, so this is basically an operator in quantum mechanics or in the Hilbert space, and then this operator, when it multiplies this wave function beta or this kate vector beta, it basically gives us the kate vector beta itself. So a matrix, when it multiplies a column matrix, basically gives us the same column matrix. So this part must be nothing but the identity matrix itself, so which we write as the identity matrix 1. Okay, now in this case we took only a set of 3 basis vectors. So if we have a set of n basis vector, then we have the general notation that summation over n psi n is equal to the identity operator. Okay, this is the identity matrix or the identity operator. So this is again a very important result, and again we use this result a lot. Okay, so as I said earlier that psi1, this one is basically an operator, this is not a number. And what does an operator of this form do? So the question is that what does an operator of this form do? Okay, so to answer in very simple terms, or to understand in very simple terms, let us take a vector in space. Okay, so we are not talking about eigenfunctions or wave functions now, we are talking about a vector in real space, and let us take a vector S which is equal to ax I cap plus ay j cap plus a z k cap. Okay, now I, j and k are the basis vectors here, so this form the basis in space. Now if I do the dot product of I dot s, so it basically gives me ax. Okay, and then if I multiply, so this dot product is basically a number. Okay, this one is basically a number, and then if I multiply it with I, so this gives me the component of the overall vector in the x direction. Okay, so I repeat again that I do the dot product of I and s, which is a number, so this gives me the coefficient of x, and then if I multiply it with I, which is again the unit vector, this total gives me the component of the vector in the along the x axis, which is basically this part. Okay, so similarly we have a wave function beta which is equal to let us say c1 psi 1 plus c2 psi 2 plus c3 psi 3, and if we do the inner product which is equivalent to the dot product with this psi 1 over here, then we will just get this coefficient c1, this is what we discussed, and then we are multiplying it with this kth vector psi 1, so this gives me c1 psi 1, so it gives me the component of psi 1 that is present in the wave function beta. Okay, so this gives me the component of psi 1 that is present in this wave function beta. Okay, so these operators of this form are known as the projection operators. So operators of this form are known as projection operators. So this kind of operators projects the actual wave function in its own direction, that is it gives the component of psi 1 that is present in the wave function beta. So this one psi n, this is known as the projection operator. I again repeat that this is not a number and this is different from the inner product, and this gives the component of psi 1 that is present in the wave function. Okay, so let us do up to here today. Thank you everyone.